Welcome, dear viewers, to the first lesson in simple harmonic motion, oscillations. Now, I could go out and just tell you what simple harmonic motion is, but that would be confusing. Simple harmonic motion can be confusing at first. I can almost guarantee you wouldn't understand it. So what we're going to start off with first is an example of simple harmonic motion, the simple pendulum. Now let's look at our friend, the simple pendulum. Let's look at him in a few different positions. Let's look up here, over here, over here. These are all the same pendulum, by the way. Pendulum is simple. It's just a string attached to a ball, goes back and forth. Now, if we look at a free body diagram at our pendulum in each of these instances, we can see that tension acts on it, as well as the force of gravity acting on it. And as you can tell, there is a force that makes the pendulum want to return here, which we call the equilibrium point. However, at this equilibrium point, the force of tension has overcome the force of gravity. It's actually greater in this particular instance, which makes the pendulum keep on going in either direction. Now, what do we actually, what does this tell us? Well, this tells us about something called simple harmonic motion. When analyzing this pendulum, because the angle, we're assuming the angle here, is quite small. So, because the angle is small, we can make several key assumptions. So, we can assume that displacement here is horizontal. Now, of course, it's not actually. It goes up a little bit, but in this case, we're just going to assume it's horizontal. I'll draw a little extra diagram to the side here of exactly what's going on with our pendulum. Now we've got tension here, got a line here, there's our angle. We're assuming the displacement here is purely horizontal. The force of gravity is acting upon it, and the string has a certain length. Now we can also assume that because it's only horizontal, that the force that makes the pendulum want to return to the equilibrium position, so the force of return, we'll call it, is the horizontal component of tension, or as we would call it, T times the sine of this angle, because, you know, there's the hypotenuse, there's the opposite, bam. There's the opposite right here, which is the force that's going down there, and yeah, so using sine. And then we can also assume that weight is approximately equal to tension. So that would mean, in this case, that the component of the returning force here is going to be same as the weight returning force. The component of tension is equal to the component of gravity in this case. Now, using that, well, it's going back, it's going in a negative direction, so we can change this to make it negative. Let's say that the returning force equals negative mg sine theta. We can also assume, using this diagram here, that sine theta equals the horizontal displacement over the length, because that's the opposite over the hypotenuse. That's what sine theta is. So if we insert that into this here equation, we get the returning force equals the negative mass times the acceleration due to gravity times the horizontal displacement over the length. And if we substitute Newton's second law, then we can get that acceleration equals negative gx over L. So, what does this equation here tell us? Well, it tells us that the acceleration is directly proportional to the maximum displacement from the equilibrium position here, and inversely proportional to the length of the pendulum string. Now, what does that tell us exactly about simple harmonic motion? Well, it tells us that as a function, it looks fairly sinusoidal. Now, what does that mean? Well, if you were to graph the displacement of the pendulum across the time, it would look a bit like this. That's a sine function, I hear you say. And yes, it is. Here, it's in equilibrium. Once you get up here, it's at the furthest it can be from equilibrium. Once you get here, it's back at equilibrium, but headed the other way. Right here, once again, it's the furthest, but in the other direction. And right here, it's back where we started. And that is the essence of simple harmonic motion, where acceleration is directly proportional to the displacement from a certain equilibrium position. That type of motion is called simple harmonic motion. So let's write down a definition, because you're going to want to remember it. SHM, simple harmonic motion, is where acceleration is proportional to displacement from a certain point and is always in a direction that points toward that point. That is the definition of simple harmonic motion. Gonna want to remember that, all right? Because now we're about to get into some terms and quantities that help define what simple harmonic motion is. A cycle. A cycle's pretty simple. That's one there and back motion. So for our pendulum, it would be starting here, going over, then heading all the way back. That's one cycle. Amplitude, in this case, represented by the variable x sub naught, is the maximum displacement from equilibrium position. Our maximum displacement. Measured in meters, of course, and if this is equilibrium, and it can only get this far away from equilibrium, then that is the amplitude. The period, as represented by t, as you may remember from our last section on circular motion, is the time for one cycle. Of course, measured in seconds. Then we have an interesting value known as frequency, which is the amount of cycles per second, measured in 1/second, also known as the hertz. And frequency is represented by a cursive F. And finally, we have kind of a key value here, angular frequency, which actually is the same as our good old friend angular velocity from our last section, measured in radians per second. But when we're talking about simple harmonic motion, it simply is the radial version of frequency. It's how many radians you covered per second, not how many cycles you covered per second. And using these values, the equation for that graph we discussed earlier, the sinusoidal graph, is your displacement at any given time is equal to the maximum displacement or amplitude multiplied by the sine of your radial displacement multiplied by time. And that's, in essence, simple harmonic motion in graphical form. Now we can also represent simple harmonic motion in one other form, which is mass on a spring. If you imagine, for a second, a spring, wah, and a block on it. Let's say this is equilibrium position. Let's say you put the spring into motion, where it can be up here, or it can be all stretched out and down here. The spring's going to go back and forth and back and forth and back and forth, and it's going to be simple harmonic motion, just like a pendulum, where this is the farthest it can be, this is the amplitude in either direction, this is the equilibrium position. It's simply the same things apply. And so those are the two instances that we chiefly use to represent simple harmonic motion. And the reason why is because these represent key waves, transverse and longitudinal, which we'll be discussing in the next video. Now, moving on. you can graphically represent simple harmonic motion in the way I described before, displacement versus time, which looks something like this. We mentioned displacement time graph, which would be, in the case, if we use the mass spring as an example, it would look like this. So this one's actually a cosine graph. And that is because if we assume that it starts at the highest amplitude, it'll start right there, then it'll reach equilibrium, then head to the lowest amplitude, equilibrium, highest. It's like a cosine graph. So the equation of this line ends up being the displacement equals the amplitude times the cosine of the angular displacement multiplied by the time. Now we can also represent it in the form of a velocity time graph. Now if you remember displacement time graphs and velocity time graphs from our mechanics section, you'll remember that the velocity time graph is simply the derivative, the dx dy, of the displacement versus time graph. So if you remember what the derivative of cosine is, you'll remember that it's negative sine. And that is exactly the case. The velocity versus time graph, for that exact same motion, we're assuming that the motion here is high spring, equilibrium spring, low spring. This is what it looks like. It's an inverse sine graph. So at here, at the highest position, velocity equals 0. Once it's in equilibrium, the velocity is the maximum. And once it's at the other maximum amplitude, velocity equals 0. It's a key thing to remember there. At the areas where the amplitude is maximum, the velocity is 0. Where the amplitude, where we're at equilibrium, the velocity is maximum. And in this case, the equation for this graph would end up being that the velocity equals the negative velocity sub naught, which in this case is our maximum velocity here. That's velocity sub naught, multiplied by the sine of the angular frequency times time. And finally, we can represent it in terms of acceleration time graph, which, if you remember, once more, is simply the derivative of the velocity time graph. Now, what's the derivative of a negative sine graph? Well, it would be the negative cosine, which it is. That's what it is. So, in this case, maximum acceleration is achieved at amplitude. But there is 0 acceleration at equilibrium, which is another key thing to remember here. And the equation for this graph would be acceleration equals negative a naught, where a naught is maximum acceleration at any one of the maximum amplitude points, multiplied by the cosine of the angular frequency times time. Now, what can we determine from this? Well, we already know, discussing earlier, that by the definition of simple harmonic motion, that the acceleration is going to be proportional to the displacement, right? Which we're making negative. We're assuming it's going down in the negative direction. And because we know, in this case, that the constant of proportionality, it can be shown, is actually angular displacement squared. So we know that this is the formula for the acceleration of a spring. So now we have two formulas. We have our earlier formula that we came up for a pendulum. And this is our formula for the acceleration of a spring. Now, there are a few more things we need to discuss before we finish with this represented with these oscillations here, and the first of which is energy that is associated with simple harmonic motion. Now, if you remember, the pendulum or the spring, it really depends. Here's a maximum displacement, here's a maximum displacement, and here's equilibrium. So there's equilibrium, or I don't have to write it. We'll just say here that the amplitude equals 0, and here the amplitude is maximum. If you'll remember, at the maximum amplitude, velocity equals 0, but acceleration is max. And at equilibrium, velocity is max, but acceleration is 0. The same is true here. Right? Well, if we're talking about either one of these, up here, it's at its highest displacement from the 0 line, right? So the PE, the potential energy, is going to be maxed out. Well, the kinetic energy in this case, because it's not moving, there's no velocity, has to be 0. Down here, the velocity is max, so is the kinetic energy. The potential energy is now at 0. Same thing is true for the spring. That is how energy relates in simple harmonic motion. Now, if we were to graph this, it would look something along the lines. If we look at the kinetic energy graph, and we're assuming we're starting from an area of maximum displacement from the amplitude, it would look something like this. If we were to graph the potential energy graph along with it, it would look something like this. No, more like that. There we go. Now, what does that tell us? Well, this gives us the total energy is constant, which makes sense. According to the law of conservation of energy, energy has to be constant. Now, there's one last thing we have to discuss before this video is over, and that is phase. That's a very simple concept. Two things are moving, and they achieve amplitude, maximum amplitude, and simple harmonic motion at the same time. Well, there you go. They're in phase. However, they assume it at different times, any different times. It doesn't have to be opposite at any different times. They're out of phase. In-phase graphs will be the same. Wah, 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 wah. Wah, 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 wah. While out-of-phase graphs will be opposites or something different thereof. And that's it. That is our oscillations video. Stay tuned. Next time, we'll be talking about the fun subject of waves and wave behavior.